welcome to Rob's Fix-It Shop. We got something really cool on the bench today. It's an hp3325a synthesizer function generator, and I bought it off eBay, and when I got it, it was not working. There's no signal coming out, and when I test it, it gives me an 8KL failure, and it says test 1 fail, test 2 fail, test 3 fail when I run the self-test, right? So there's something clearly wrong with it, so we're going to open it up and take a look at it. I talked to the guy who sold it to me, and he gave it to me for a much cheaper price. So it's perfect. We're going to take a look at it and see if we can get it working. Okay, so let's just take a look here. And it's got these nice clicky keys, right? And it's got the sweep function. That's why I bought it. I was interested in the sweep function with the ability to have the X scan from an oscilloscope driven by the sweep itself, and this has got that. So I thought that would be cool. Looks like it's got a sync out and a signal. And let's take a look at the back. Yeah, so this is one of the things that's so cool is it's got all these different things that you can connect to in the back, and a reference, a marker for the sweep. This particular model has option 1, which is a 10 megahertz oven controlled oscillator for the reference. And so yeah, we got all kinds of fun stuff going on back here. Oh yeah, that's beautiful. So yeah, here's our power supply. Get some interesting transistors over here on this heatsink. I think this is the GPIB board, logic and computer board, and then this is the synthesizer here. And I think we can get into the bottom as well. So I guess step 1 is to check the voltages in our power supply here. So if we put one of our screws here for ground, then we got our 15 volt test point, and we've got 15.37, and then our minus 15 is over here. And the minus 15 is the reference, and then we got a nice 5 volts too. And so that I think we can adjust that 15 here. We can do it just for fun. So I think if we get on that minus 15 test point, that doesn't look right. And I think if we turn this guy here, oh, that's nice. Look at that. Now if we go over to the 15 volt, pretty close. And then 5 volt. I went up a little. So anyways, that's cool. But it's this this guy here that I'm worried about, right? Is that if I look at the power going to these guys, right? There's no power going to them, and no power coming out of the voltage regulator. And the funny thing is, if I look at there should be something going to the voltage regulator, and there's nothing going to the voltage regulator. So that would mean that it's either this rectifier bridge here or this capacitor shorting it out. But the thing is, if the capacitor were shorting it out, then you would think that if I switch to AC here and look at this, you would think that would be kind of shorted out. But we got a nice 9 volts AC coming into there. So somewhere between here and here, we're losing all our voltage. So we have 5 volts coming into the chips in. And one thing I might have screwed up before, or I know I screwed up, is that we're not grounded to the case here, right? So we have to find the ground there to see the voltage. So who knows, maybe it was working all along, but this whole area here, it's got these optos here that are isolating this area here, this GPIB, from the rest of the system. So looks like it's working. Okay, so here's the service manual, and it says to go to service group J if we're not getting a signal out. And so here it says the amplifier circuit, well, let me make it bigger. The amplifier circuit supplies sine wave current to the output amplifier. Disconnect the cable marked 23 ALC to permit maximum signal amplitude at 814 test point S in. All right, I can do that. Okay, so I've disconnected 23 here, and then I have on the test point amplifier in, and I'm not getting anything. I don't quite understand that. I guess before we go too far, let's check the voltages here. 15, minus 15, and 5. Well, they all look good. And there's a couple of fuses. I checked those. Those are good. I was just kind of looking over here. This is the oscillator here. It's quite the production. Anyways, I just put my probe up to the 10 megahertz output. And look at that. It's exactly 10 megahertz. That's cool. So, somewhere on this board, I think. Okay, well, I seem to have learned something very important here. So this model comes with option 1. And option 1 is this special crystal oscillator that's in an oven, right? And for temperature control. And when you have this option, this is the reference signal for everything else. And you need to feed this signal into the circuit, but you can't just do it. It's not just done inside here. It actually goes from here, and then this leads outside the device, right? So if we look over here, and it's upside down, obviously, but there it says option 1. But here's the 10 megahertz of an output right here, right? But that has to be fed into the 10 megahertz external reference in. So I've got my little cable here, so this has to go here to here. Now, it still doesn't work, but without that in there, it never would have worked, right? So that's an important thing. You know, live and learn. I should have read the manual first. So then if I pull my external reference right here. You can look at the scope. And I've got a nice 10 megahertz coming into this board here. And so, now what? I don't know. I'll have to look around. Okay, so our reference signal comes in here. Looks like there's a couple of diodes here to kind of keep the signal from going too high. Comes into this little op amp. That's one of those little tin ones. And then it goes here, and it looks like these are just acting as buffers. Yeah, I'm not sure. It looks like you got a little inverter here. I don't know what for. And it goes into this transistor here, through here, into this guy here. And then over here you've got TP2 reference tune, right? So let's just take a look along here and see what we can find as far as that signal coming out of Q3 into Q2 and up to this test point, out of this op amp into the test point. So I'm going to do this as best I can, but here's where our test point comes in. We've got our 10 megahertz signal. It comes over to this op amp right here, and then over to this transistor right here. And coming out of this transistor, you know, we're still looking pretty good. We still got our 10 megahertz, right? And then I believe it goes over to this FET. Right, and then what that's, I don't know what test point that is, but we still have our signal. It's kind of mangled, but I don't know if that makes any difference. And then it comes into this op amp here. So it looks like we can follow. So I think this here is acting as a current source, and I was wrong about this test point over here. This is just acting as a current source for this guy here, and then that comes, this 10 megahertz comes over into this chip right here, and then so this is, if I look at pin 6 on U2, let's take a look at that. So this is U2. So we go 1, 2, 3, 4, 5, 6. There we've got a nice 10 megahertz signal, and then also if I come over here and look at the 30 megahertz, that looks good, right? And so I think this board is working. I guess that's what bottom line here. Okay, so a little theory here. We have to learn a lot on this thing. So that 30 megahertz, if we look here, that 30 megahertz here that we're getting from the from that crystal oven, that comes in and gets divided by 300, and then that produces 100 kilohertz, right? And then you have this voltage controlled oscillator up here, right? And it's going to be divided by some number, right? Well, the number is set by that little computer in there based on what you type into the screen, right? And so if the number here is 400 and you're doing a phase detection, right, it's going to look at the error between this and this, and it's going to, if there's an error, it's going to up the DC voltage, right? And so this voltage control oscillator is going to, let's say you're too low, it's going to increase the voltage until that oscillator, until these two signals come into phase, right? So there's two different signals that we're looking at here, right? We've got this 30 megahertz, we're dividing it down to 100 kilohertz, and then this frequency that the VCO is putting out and dividing by some number n, right? Which should be 100 kilohertz as well, right? So we're going to be comparing these two values, determining the error, adjusting the VCO based on that error, and then when the VCO is at the correct frequency to line these two waveforms up, then you've got this mixer right here, right? And that mixer is gonna, it's like a super heterodyne on an old radio, right? It's gonna take the 300 or the 30 megahertz and then what's coming out of here, which would be 40 or 50 or 60, and it's gonna mix those two guys together here, and the difference frequency is gonna be this one is set to 10 megahertz. This example is set to 10 megahertz, right? And so that's what that PLL is doing, is it's figuring out what that frequency is. So we've got to make sure that our VCO is working, that our divider's working, that we're getting our reference voltage, that we're comparing them properly and adjusting the VCO, and that when we mix them, we end up with the difference. And so if I come over here, right, here's kind of a block diagram of that happening. So the fractional synthesizer here, let's see, the fractional synthesizer, that's what takes that number from the computer and kind of produces our initial voltage or our initial frequency. This is from the top part here, right? And then we've got coming in from our external reference, which is that 30 megahertz clock, that comes into here, and into here is divided down. And when it's divided down, it goes to 100 kilohertz, right? And so that in here then is where you're comparing that 100 kilohertz with the 100 kilohertz based on the frequency coming in, and you're outputting that resulting frequency over into here, right? And then that puts out that frequency here, and then you get the frequency from the reference frequency, you mix them, and based on the mixing, then you end up with this sub-frequency, or the frequency that you typed in the front. And from there, it goes over to our function circuits, right? So what I'm seeing is, I'm seeing a good 30 megahertz, right? And let me show you that. So our reference is coming in right here, and it is, it's, let's see, I figured that all out before. Yeah, your reference is coming in. It's going through some, it's going through this little transistor here, in through here, and then there's a little op amp here, and I think this is acting as a bit of a buffer. And then it comes down into this test point right here. So let's look at that. So if we look at that test point, we've got this beautiful 30 megahertz signal, right? So that's good. So if we look over here, right, that's our 30 megahertz, and I'm not sure where this reference divider is, but I suspect that that is that 100 kilohertz output, right? So this part we know is working, right? So then if then we want to look at this VCO and see if the VCO is putting out a frequency. Okay, so here's how we're going to test the VCO, right? So it says to pull the cable at J18 and program the front panel for 10 megahertz. Pull the cable and place an external DC voltage to the VCO and monitor the waveform at pin 6. Alright, so let's do that. It took me a little bit to figure this out, but let's take a look. Okay, so this is, let's set it to 10 megahertz. Okay, that's where we're at. And if I put this here, so this is U1, 1, 2, 3, 4, 5, 6. Oops. Get our ground a little bit closer. And we're right at 100 megahertz. Now what it says to do is to pull this, right? And then attach an external power supply. And I have that external power supply set at about 5 volts. And apply that right there. And so it just says it should approach. Hang on, I'm going to figure out something better for this. Okay, that's a little better. Now let's go back to pin 6. And it just says as I vary the voltage, you should see it approach 100K. So, I don't know, I guess it's doing that. It's staying right around 100K. So, okay, I think that passes. And then, let's take this, put this back. And the second test is, so if the frequency of pin 6 approaches 100K and the problem appears to be digitally reliable, blah 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 blah. Okay, disconnect the power supply, did. Leave cable disconnected. Measure and note the frequency of the VCO signal at jumper W3. And I think that's, I couldn't really find a thing that said W3, right? But I think that's right back here. If I go like this, and hook my scope up to that, okay, so I pulled the cable right there, and I think that's our VCO output. And then it had me pull the input, and so it said that if you do that, it should be around 45 megahertz, and that looks pretty good, right? So it goes into a lot of more detail on the testing. But the thing I want to see is that if I connect this back up, right? That example that I showed earlier said that the frequency would have to be 40 megahertz for 10 megahertz. So it's set to 10 megahertz on the front, and we're seeing 40 megahertz. Let me make that a little bit bigger. (40 megahertz here. So if I wanted, let's say, if I wanted 5 megahertz, then that should be 35, right? So let me set it to 5 megahertz. And there it goes to 35. So I think the VCO is working great. So what the heck is going wrong? So if the VCO is putting out this signal, and this signal, so this signal needs to be mixed with the 30 megahertz signal, and that happens over on the other side. So let's take a look at that, because this seems to be working pretty good, I think. So the signal from the voltage controlled oscillator, that comes in right here, and I've got my probe hooked up, and I've got it at 5 megahertz. I'm set, and I've got 35 megahertz here, right? So I've got that, and I've got my 30 megahertz here. So here's what's got me flummoxed, is that signal coming in here, signal coming in here, goes into this magic black box right here, and it should come out right here and come into our signal amplifier all through here, and it is not. And I'm not sure why. One thing that might be the case is that if I put out a so this whole high accuracy thing works up to 21 megahertz, and then after 21 megahertz you can't get the signal out the front, but you can get a signal from 21 up to 60 megahertz out of the back, and that does work, right? And so I think there's something in here that must switch that. I think that's this line right here, right? And so if I put my scope probe on that, I'm not getting anything until, let's say I'm at 5 megahertz here. Okay, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And then I'm not grounded very well. So that right at 21 megahertz, it does switch over to here, right? And I think my scope probes are attenuating it, but yeah, you can see I'm up to 45 megahertz. And I think that's the voltage controlled oscillator. They're using that to generate that signal. So that's coming out here. So let's pull this case off and let's take a look in there and see what we can see. Alright, so our signal from the VCO is coming in here. It needs to end up in here. But I think what it does is it goes into this chip here, and that if the frequency is above 21 megahertz, then it goes out this and out to the back. Otherwise it goes out to here, right? And that's one thing I want to check. I want to see if that's working right. And so if I go over here, so here's that whole circuit, and you'll see that it comes in here and then splits out, and one, let's see, so then the signal comes all the way, whoops, signal comes all the way through here, then it splits off right here, and this is kind of a control unit for if the signal is 21 megahertz or above, and then that switches that, and that goes out to the back. See if I can slide this over. Yep, goes out to the back, and the other, and it splits the signal. The other half of the signal comes through this U17 pin 9 and 15 And so that's what I want to look at, is pin 9 and 15, and see if there's a signal coming out there and going to the mixer. Okay, so we're going to look and see what's coming into the mixer then. And so this is the mixer. I took the metal can off of it, and here's a chip that kind of selects whether it goes to the back panel or to the front. And if I look at here coming into the mixer, you've got 35 megahertz, right? So then I want to see on the other side, I should see 30 coming in on this side. And there's just 2 wires coming in there. So if I look over here, so I've got my test point there, and then you would think it would have to come in on one of these 2 wires right here. Nothing there. Nothing there. I mean, there's something there, but junk. Yeah, I'm going to have to look at how that signal gets from here over to here, because it really feels like it's disappearing from here to here. I don't know. Okay, I'm going to see if I can get the schematic for that and take a look at that. Okay, so here's our test point right here, and then we're coming through into a differential pair, and then out of that differential pair, U14, it comes over here into the mixer. So this isn't going to be anything. This is almost like a constant current source, maybe? I don't know. Okay, so we're going to be coming out of... Okay, well that's handy. Going into 4 and out of 7. So into 4, okay, that's good. And out of 7. Okay, so there's nothing coming out of 7. So I thought I'd sleep on it, and so what we're seeing is we've got this differential pair here, and I think, and I'm not an electrical engineer, I just like fixing things, but I think what this differential pair is doing is it's driving, should be driving like this, and then maybe the inverse, right? And doing a differential pair, the communications of the signal into the, this goes to the mixer, right? And but we're not seeing anything on either one of these lines here, right? And we should be seeing a waveform on each one of them. So that could be that this is in a DIP or an IC, right? This differential pair, which is good, right? Because then all these components are well matched, and so it's not just a differential pair, but then it's driven by this this here that's kind of driving the current, right? And this thing is driven from this multiplier here. So let's look at that a second. So if we look way over on the left there, we've got an input of the sine amplitude, right, and the amplitude of the VCO. Okay, and I think what this is doing is it's turning on modulation, and so here we see this kind of this analog switch right here, right, and that's switching in this line, right, and yeah, so it's switching in this line, and I think I'm guessing this whole thing is to do that modulation, and to kind of do that, then that's coming all the way through here, and into here, right, and then what that's doing is that's modulating the current that's going into creating this signal right here, right, and but the problem is we've got no signal here. So that could be that this is not being held high enough to allow current through here. That's one thing, I think. The other thing, this signal looks pretty good coming into here. The other thing too is that here this line is kind of interesting. It looks like it's got a zener down here, right? And that zener is to limit, I think, to limit the voltage coming through here to 10 volts. But I'm not sure. I mean, like, you know, and if that were bad, that could be allowing this too high. And if I'm thinking right, I think if you ground this pin, you should get the waveform through here, right? And but I'm not sure. So what I'm going to do is it might be the chip, but it would seem sketchy to me that would go bad just because it's not a high current thing going through there, right? Anyway, so let's try, the first thing I'm going to try is I'm going to try grounding this and see if we see our signal appearing over here. Because we are seeing the signal coming in over here, right? And at 4. And if we ground this, I think we'll see all the current flow through this side, and we'll see this. Maybe. We'll see. Alright, so I'm going to try that. So I had to redraw it. I wanted to redraw it with the pins in the correct place. And this kind of shows the circuit of the 30 megahertz coming in here. Then it's kind of branching through here. It looks like it's doing a little filtering. Here's that Zener diode and a voltage divider between 15 volts. So it would be kind of interesting to kind of look here and see what's coming into here on pin 11. And yeah, so let's see that. Let's look first what's coming through here, and then let's try grounding this out and see if the signal then comes through here and through here to the mixer. Alright. Okay. So the first thing we're going to do is we're going to look at pin 4, right? And see that we've got signal coming in. So if we go to 1, 2, 3, 4, and we do. We have our 30 megahertz signal, right, which is just what we want. Now let's look at the output on pin 7, right? And on pin 7 there's hardly anything coming, I mean just garbage coming out, or just very low signal coming out, right? And so then let's look at pin 13. So there's nothing coming out of that other side either. And for some reason 13 and 16 are connected, but if we were to, let's look at what we've got coming into 11, right? So 8, 9, 10, 11. So we've got nothing. So we've got nothing coming in through here, right? And okay, no signal. And so let me try just grounding that, and let's see if then by grounding this side of the pair, if that switches this one on and we start to get output. So this is going to be a little dicey, but let's see. Okay, so I got my voltmeter ground, and so that's going to be grounding pin 11. That's by grounding pin 11, that's going to force all the current through this side, and we should see that line come high, right? And so that's out pin 7. I'm going to put this on pin 7 first. Okay, and then 8, 9, 10, 11. Okay, so I don't see anything happening there, right? So you would think that that would work. So the other thing too is that if this, let's check to see if this transistor is on, right? Because this, let's see, this is, so this goes to ground here, right? And so we need to be 0.6 volts above ground to switch this transistor on, because without that transistor there's no current flow through here, right? So let's check our voltage at pin 8, 9, 10. So 8, 9, 10. So that's strange. So I've got minus 11 volts. So I think at minus 11 volts, this guy will never turn on, right? And it will never kind of provide the power for this. Yeah, because this modulation circuit, yeah, it's complicated. Alright, so let's take another look at that modulation circuit. Okay, so here coming out of the multiplier, I don't know what that multiplier does, right? Probably just, I don't know, whatever. So it comes into this op amp here, right? And so we've got plus 15 volts and minus 15 volts. And then this is, so this would be feedback. So this is actually working as an amplifier, I think. So I don't know, so it'd be interesting to look at 2 and 3. Well, let's look at the test point first, right? Because the test point has kind of a note over here, and I don't get, so these voltage levels are useful in troubleshooting amplitude problems. So 1 kilohertz, test point ACD grounded, but I don't know what test point ACD is. Right? I have yet to be able to find that. Alright, so our test point is saying that it should be 1.8 volts, right? And it's not, it's a negative voltage. And so I'm going to try just forcing this to 1.8 volts, right? And seeing what happens. Alright, so I have my power supply set to 1.8 volts, and I'm just going to touch that test point, and I have the probe hooked up, and look at that, 30 megahertz coming into the mixer, finally, right? So so the question is, why? I mean, why? So I don't know. Let's assume that, let's just say for a second that what's coming out of here is good. It could be this here, right? It could be that maybe this is not working right. I don't know. So according to my calculations, this voltage divider, if this is 0 here, then we should have 1.8 volts, or 1.9. What did I write down? 1.9 volts, right? And so with 0 coming out of here, yeah, so with 0 coming out of here, but I think what might be happening is that, yeah, it could be this. I don't know. Maybe the pot is just screwed up. That seems sketchy to me, but. Alright, so I got the new part soldered in. I just got a couple of screws in, so let's turn it on. Okay, so I've been screwing around a lot. I've been kind of messing with this here, and I can put resistor values in here that raise this up, that we start getting signal through here, but the problem is that it still fails all the calibration stuff. And so I think today I'm going to take a different take on it. I'm going to put this op amp was fine, right? The new one I put in tests exactly the way the old one did. I don't quite get that, but whatever. It's all about getting this voltage here to this 1.8 volts, but I was experimenting with this this biasing that's happening here. But I'm going to put all that back the way it was, and then I'm going to check this sine amplitude and see what's involved with, if I got to figure out what's going on with this circuit. So that's what I'm looking at next. Okay, so I'm going to start looking at this sine amplitude line, right? And so my thinking is that the sine amplitude line and this here, I think this is used for modulation, and I think this is how much signal we want coming out of this oscillator, right? Which kind of surprised me, because you would think this thing would put out just the same level all the time, and then at the amplifier it would be adjusted, but apparently not. So we're going to look at this W23. So now I've got the so I've got it pulled, right? So once you pull it, then I start to get a signal out. So I'm looking at what the voltage coming off this amplitude, this sine amplitude is, and it's 0.6 volts. And so I'm going to go to the front of my panel and slowly increase. So it's 1.1, 1.2, and so as I'm changing it, we're not seeing any change. Oh, okay. Yeah, so we're not seeing any changes in that signal as I change what's on the front panel. So I think that so I don't know whether that change happens here or whether that change happens over here on this board or this board. You would think that if it happens over on this board, right, we would see it and we're not. So it's not like this board is communicating. So I don't know whether this board is communicating over to this one what the amplitude is, or if it's coming the other direction. And I don't see it changing. Yeah, it never seems to change over here, but if I look at my connector, right, so you would think that one of those two would change. All right, so let me do a little more reading. Okay, so here's the thing I'm trying to figure out. So on this machine, there's different, on this machine, the computer spits out digital values for level, offset, X drive, amplitude, and DC offset. And right now, you're looking at on this. I'm looking at. If you look at the voltmeter there, I'm looking at the value of amplitude. And if I go to the service manual, right? It says amplitude should be ranged from -4 to +10. It's showing -10, right? And it should be showing one of these values here. Okay, so let's take a look at this circuit right here. So if we look, there's a number of different voltages that we need to do digital analog conversions to, and they're right here. They're DC offset, the amplitude, the X drive, the DC offset error, and the level. I think level is used when it's doing its calibration, but amplitude is the one that we're seeing is messed up. And so what's happening is, if we come over to this part of the circuit over here, this part that I've got circled right here, that's the D to A converter and the interface to the computer, right? And then that output comes into this current source. And then if we look, there's this digital analog integrator right here. So this guy's going to be, you see it's got a capacitor right here and then a reset right here, right? And so what happens is, as this pulse comes up, right, this capacitor is going to be sucking up that charge and making it available over here. And then as our clock exceeds here, it's going to reset the capacitor so that when the next signal comes in, it can fully integrate that, right? So this guy is going to be integrating every one of the different values that I talked about earlier. And so it's all going to be based on that clock, right? And so these are the different voltages, these are the clock signals, and those are going to be integrated right here. But after they're integrated, then they come down here, and there's these sets of electronic switches, right? And those switches, they're going to be going to this one first, then this one, then this one, this one, this one, and this one. And so that if we want our X drive, when the clock signal for the X drive comes in, it'll flip the switch closed, Here we got another capacitor and op amp, and that's going to be integrating that voltage, and then this shuts off. That's going to hold that voltage and be available for the rest of the system. And so that's how we're using one A to D converter, and we're using it to produce 5 different voltages, and it's happening very fast. This X drive, that's the output, that's the trace output to an oscilloscope. So these things, this is going to be happening pretty quick. I think there's like a 1 megahertz clock that's running it. So yeah, so we're going to be taking a look at this circuit. So coming out of our A to D, our signals are all full. And my understanding is that we should see those squashed down for different values, right? And so that let me try switching the DC offset. Oh, are they coming up? Oh, they might be coming up from the bottom. Yeah, it doesn't seem to be changing much. Right, because it looks like 1, 2, 3, 4, 5. No, I don't know. Yeah, I don't know what's going on. So that if I go to Amplitude and I move that up or down, yeah, you would think those would change pretty drastically, because these are the pulses that are going to be going into the integrators. So this pulse is going to be, is going to go through that one of those electronic switches, go into the integrator, and be integrated, and that's going to produce the voltage coming out. But these should be moving a lot, right? So yeah, so I don't know. Okay, well, I'm going to look around some more. Yeah, if we look at their drawing here, they say the DA digital analog converter integrator out. Which is this here, right? So that's this guy here, and that's at test point. Here, it's saying minus 4 volts. And, oh, okay, so we've got 6 pulses. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. So we got 6 pulses, one for each of the different values. Yeah, I don't know. So I'm seeing, let's see, you can see my mouse. So I'm seeing good voltage here, minus 10 here. So this should just, this is the integrator, right? So this should be charging up this capacitor and then discharging it with the switch right here. So I'm going to get good signal in here. These two values are right, but the values coming out of here are too high, right? And because they shouldn't be above 0 volts. And so I'm going to pull this resistor and see if it must be something over here that's causing the problem. I'm just guessing, but I'm going to pull that resistor and see what happens. Hello? Okay, so one thing we saw that the levels of the pulses that are going towards building up those voltages for the different parts of the board, those levels are way too high, and sometimes they're in place and other times they just kind of rise up. And here's something I found in the service manual. A common problem with this section of the A14 board is loading of the DAC test point by a bad analog switch, op-amp, or sample and hold capacitor. To check for a loading problem, unsolder the lead nearest the DAC test point on the resistor R55 between A14 U16 pin 6 and the test point. Attach an oscilloscope probe to the unsoldered lead of the resistor and monitor the DAC pulse train. Continue to observe this pulse train while pressing the resistor lead down so that it makes contact with the point from which it was unsoldered. If any change in the levels of the pulse train is observed, the waveform is being loaded by a defective analog switch or op-amp. And yeah, so let's take a look at that. Okay, so these are the slices, these are the voltages that are being pumped out through that switch to the different integrators. And you'll see, yeah, this one's a little bit above 0, but it should be from 0 to minus 10.6, and we are minus 10.6. I don't know why we're a little bit above on the other side, but now watch when I attach that probe. So this is the resistor I've lifted right here, and so this stuff, so the first integrator, the main integrator, is right here. That's what's creating these pulses here. And then that circuit comes into this resistor, and from that resistor it feeds out to the different electronic switches, right? The electronic switches are switching on or off depending on which one of these the actual output is looking for. And so if I take the resistor end and then just connect it to that probe, we see then that our output is going all the way up to about 10 volts. So we're going from minus 10 to 11.2. I'm thinking that might be an op-amp because the op-amps have that higher voltage going into them. But we should be able to pull up the resistors on each of those different outputs and see which one is causing this behavior. So that's what we look at next. So here's our main integrator right here, right? That's what we have our scope hooked up to, and that resistor's right here and the test point right here, right? So if I pull this resistor, it disconnects this whole line right here. So really, so let's say we're talking about the amplitude, and that's the one I'm going to test first. Amplitude comes through here, goes through this electronic switch right here, and then goes to this op-amp, this U23, right? And then here's the capacitor for doing the integration, and a little dropping resistor. So I think if I pull this resistor, if this is the one that's screwing up, then I should be able to, well, I might be able to just look at this line here and see if it's got high voltage on it. I don't know. Okay, I'm gonna pull this resistor and see what happens. And so that's a 1K by U23. Or actually, it's, I know I'll forget, it's R67. It should be over here. I don't know if this makes a difference, but I looked at, if I look at Amplitude, it's right at 0, and it should be 4 or -4. But then if I come over here and I look at this one here, this OS1, it is 10 volts, right? So I would be suspicious of this one first. So I'm going to try pulling that resistor. So the switch is right here at 10. And turn it on. So 10 at the, so the pulse is coming in on 13. No. The pulse is coming in on 9. Pulse is coming in on 9, and the output's coming out on 10. Okay, so then see, coming out of the switch, so the trigger going into the switch is 9. Seeing that, that's beautiful. And then going in is 11, which looks good too, because that's going to have all the pulses on it. And then coming out would be 10, and we're just always low there, but I'm going to see if I can pull that resistor low. I'll just do it for a second. But then you can see that then the integrator's working, right? Because that capacitor's still on there. And so so I'm gonna bet it is that op amp there. And I'm gonna bring it over here. There's one other thing I wanted to show you. There's a little tiny mark on the top of it, so I don't know, that's kind of small to be burned out or whatever, but we'll replace it and see what happens. Okay, so I kind of screwed something up. This is not an op amp. It's actually, well, it is kind of an op amp, but it has the pin 2 internally tied to the output, and it's like an LM310 or something, but I don't see where you can buy any of those. But I did find somebody else on the internet who had replaced this with an op amp and then just tied pin 2 back into here. I actually went online and I found some of the original chips, and I'm going to replace this with one of the original chips because I just replaced it with an op amp, and so that's what I'm going to put the original chip in there and see if it makes a difference. So live and learn, but I might try later to replace that with an op amp and just see. One thing is that these voltage followers, I think they're called, they react very quickly, right? They're like 10 megahertz, and an op amp I think is like 3 megahertz that it responds, but I don't know, for this kind of work I don't know that it makes any difference. So yeah, so I'm going to put in the chip that I bought, get rid of that one, I really screwed up there, and then we'll test it out and see how it works. Alright, nice parts if you can get them. So I had this crazy dream that once I got that the integrators fixed, that everything would be great, and it does seem like the integrators are working pretty good because I can check those voltages and they all look right. Where before they seem to be kind of off in a weird way, but I still don't have a signal, and so I'm back to service group J, and what it's saying is that when you connect to the sine test point, you should have approximately 200 millivolts peak to peak at the selected frequency, right? And if we look at our scope, we don't have any, we just have noise on it, right? And one thing they say to do is to, this 23 ALC, I think that's the automatic level control. And so here I can pull that off, right here. Get that out of the way, and then still we started getting a little bit of signal here, but it's a little bit better, but still there's just hardly anything, right? And if I connect directly to here, right, I am getting a signal, right? It's set at 1 kilohertz, but it's just 20 millivolts peak to peak, right? Almost nothing. And so that got me thinking that I've got to come back to this mixer and find out why this isn't working. And one thing I'll also say is that when doing this kind of testing, you have to have this sine amplitude disconnected, and you need to ground this test point right here. These are both used to adjust the level automatically, and if those aren't set right, then you're not going to get the proper voltage into this guy. We talked about this earlier, this differential pair there. You're not going to get the right, you're not going to get a decent signal into here, so you'll never get your 30 megahertz into the mixer through here. So again, let's look at the mixer again. So a couple of things when looking at the mixer, and this stuff I figured out. One, you want this this grounded, right? Then you want this jumper over on test, not on norm, and you want the automatic level control disconnected, right? And then you should be able to see, let me get my scope probe here, right? Then you should be able to see coming in do I have my right? You should be able to see your signal coming in from the fractional end divider, right? So this is your signal there, and then you should be able to come over here and see the differential signal of coming. I mean, yeah, I'm not there. You should see that signal coming in. So that's 30 megahertz. The other one's just slightly off 30 megahertz. And you should be able to see both those signals coming into the mixer, right? They're coming into here and they're going through this weird rectifier and thingy. And then what they do then is they come through, I think, this little channel here, and eventually they end up in this little thing here, which is, it's an NPN, it's a it's 5 NPN transistors on a single substrate, right? And so that they're all kind of closely temperature matched. And that's this chip right here. And what this chip is this chip is the amplifier, right? Is the amplifier for the mixer, and that's amplifying the signal coming out of the mixer. That goes into here, and that comes over to the sine thing. And I want to show you what's going on there. So here's that chip right here. And here we've got test point 6. This is our signal coming in, right? And test point 7 then, not sure what that is, but that comes through this differential pair out here into a bit of an amplifier, and then comes out mixer out, right? And here these two I think are just acting as constant current sources for this differential pair. And so it looks like they've used 4 out of the 5 transistors in that chip, right? And here's that test and norm. That's so that putting it into test means that you're not going to I don't think you're using feedback then, but I don't know, whatever. So if I come back up here, and so remember, so here's that U15, here's the test point 6, and here's the test point 7, right? And so if I come back up into the diagnostics here, okay. So failures on this portion of the A3 board are usually linked to these 3 parts, and A3U15 is one of them, right? That's that U15 right here. Okay, we're back. So we want to ground the auto calibration disable, which we have, and cycle the power, which we have. So when we put 10 volts peak to peak, the voltage at test point 6 should be 100 millivolts peak to peak with no DC. So let's check that. So if I go to test point 6 right here, and I go to, let me make sure I'm grounded. Whoops. So if I go amplitude 10 volts peak to peak, right, we have our sine wave. And then it says to check this resistor here. It's fine, right? It was exactly 200 ohms, and so that was fine. And then it says the voltage measured at A3 TP7 should be the same as A3 TP6, right? And if this is the case, then A3 U15 is probably good. Well, let's check those. All right, so here's 6. Right at 0. And 7. It's close. We're about 60 millivolts off. Right? But the thing is that, so that doesn't give us much of an indication. So now look, let's say the mixer's output signal leaves the A3 board and enters the A14 board. 14 as a as a current via cable W24. A check of this current is made by connecting AC to ground, move nor test the jumper, right, which we've done, program the front panel to go sine 10 volts, we have, remove cable W24, we have, place an oscilloscope on J24 center connector. The signal should be close to 2 volts peak to peak. Well, if we look at that, we are nowhere near 2 volts. We're at 17 millivolts, right? And there doesn't seem to be much in between what's coming into that chip and then what's coming out of it, right? So I thought I'd do a little check. And here, let me shut it off. So if we look at, let's look at this one first. So the base is 4. 1, 2, 3, 4. And then 2 and 3 are the emitter and collector. Right? That looks good. And if I go the other way, obviously, should be 0. Right, so that one's good. And then 8 and 7 and 6. Right, something's messed up there. Then if we go the other direction, yeah, something's kind of messed up there. That could be some of this other stuff, but let's look at this one. So if we have pin 9 and 11 and 10, right, that looks good. That looks good. Then let's check the other way. Yeah, that could be something else, but yeah, that could be one of these accessories, I don't know. And then let's look at 14, 13, and 12. So 9, 10, 11, 12, 13, wait, 9, 10, 11, 12, 13, 14. So 14, and then here, that looks good. That looks good. In the other direction, nothing, nothing. So that one's good, right? So this one, I'm not so sure about, right? One of them's not even being used, so I'm not sure which one that is. But so then also if we go to 15, right here, we should be able to go here, and there's nothing. And then here there's nothing as well, so there's nothing coming through that at all. And oh, I'm wrong. So it's 15, should be here. That's good. And then here, and that one's good. Right? So it looks like this transistor down here is messed up. So I ordered some parts here. It's a CA3127E chip. They don't make them anymore, right? But yeah, I think I could have probably just replaced it with discrete transistors, but these are all on the same substrate, and having a differential pair, having them tightly matched like that, I think is going to be kind of important, and they're very high frequency transistors. So when I get those in, I'm going to try trading this out. I don't know. We'll see if that makes a difference. It sure ought to, because coming out of here, we're supposed to have 2 volts peak to peak coming into here. And like I say, we're seeing about 100 millivolts. So something is really messed up in this area, because our signal's good here. Something's messed up in here. I don't know. I suppose it could be those transistors there, but okay, so we're all set up again. So I got everything back together, and again, we're gonna ground our ACD test point, move the norm jumper, program the front panel for 10 volts peak to peak, remove the cable, and check to see that it should be 2 volts peak to peak, and with 2.2 volts DC. So man, I sure hope this works. I mean, it'll be a miracle, but okay, so let's switch it on. And then we'll go amplitude 10 volts peak to peak, and let's just check our .30 megahertz first, make sure we got our signals coming in. There we go. 30 megahertz looks great. Then let's look over here. There's signals coming in. Okay, that one looks good. Alright, moment of truth. Wait, first let's do the test point 6. That doesn't look so great. Mixer out. Oh, there we go, there we go. I don't quite understand that noise. And then let's go to the other test point. Now I got a signal coming out of there. And then let's look at 24. Oh my gosh, we've got signal. About 2 volts peak to peak. That is fantastic. I can't believe it. Well, let me... okay, I'm going to hook up this board to this board. And, man, I might have fixed it. I can't believe it. Okay, so now let's look at our sine test point. Good signal coming off that. And so I'm going to reassemble this guy here, and because that was the problem. Okay, watch this. came up, no calibration problem. Do my self-test. Oh, pass! Sweet. That's just great. Okay, so I'm gonna, but otherwise I'm just thrilled. I just can't believe it. All right. All right, so there it is, all back together. It was kind of a long journey. I mean, I bought it thinking it was working, and then got it for quite a bit less because it wasn't. I've never been in one of these before, but it's a beautiful machine. I mean, the way it's crafted inside, all the gold traces, it's just it's really a fun machine to work on because it's so well crafted and designed. And the service manual was very good, had a lot of tips for how to fix things. I kind of went the long way, but like I say, the service manual is very good. So let's crank it up, and let's say 3 megahertz, amplitude, 5 volts peak to peak, and there you see it up there, beautiful. And yeah, so I mean, the thing I really got it for is this sweep function here, because the sweep function will has a you can plug into the back, and it'll actually give you your scope, the X, as it's going through the sweep. And so I want to use that. I want to play around with filters in radios, and so I could set a start frequency of 1.6 megahertz and then a stop frequency of 1.8 and a time, let's say 0.02 seconds. And yeah, and there it's going. Here, let me go a time of 1 second. I don't know if you can see that up there. So, oh, and the one thing I wanted to also show, I think I showed it earlier, but you can do your tests now. Pass 1, 2, 3. And for the service manual, like I say, the service manual was really good, but it never was very clear about passing 1, 2, and 3, what they meant. But yeah, well, I hope you enjoyed the video. It was more about me figuring out how to fix it than a tutorial on how to fix it. But if you enjoyed it, hit like and subscribe, and thanks for coming along for the ride.